All right, so I'm not going to get super deep into Fourier analysis. This is something that you'll learn more about in signals and systems. And as you move further on in the EE degree, Fourier transforms, Fourier series will become very important. I don't want to get too far into that, but I do want to provide some context for filtering. And so a couple of good examples here. So when you look at what's called the Fourier transform, or the fast Fourier transform of a signal, basically the fast Fourier transform of a signal tells you all of the frequencies present in that signal, and it tells you what the amplitudes of all those frequencies are. And so you might be wondering what the heck I'm talking about, but let's just say that this is the amplitude of the signals, and then frequency is on the x-axis. And let's say I have some kind of a signal, let's say a tone, that looks like, well, what we want it to look like is a sine wave, right, at, let's just say 1 kilohertz. So at 1 kilohertz, we have this spike on our Fourier transform. It might look like this. They'll just put a spike there on the Fourier transform. Shoot, I'm drawing this terribly. Let's just draw it like that. And so that has some amplitude. Let's just say amplitude A. But unfortunately, when you recorded this tone or whatever signal this was, there was some noise, higher frequency noise, that got recorded as well. And let's say that that noise is, a much lower amplitude, amplitude B, and it's out at something like 100 kilohertz. And so then there would be another little spike on your Fourier transform that looks like that. And what that noise would look like, and what your overall signal would end up looking like, is it would look like this. You'd have this noise on your original sine wave. So this is the signal that you would end up with. And who knows what that might mean for whatever your application is, but what you originally wanted was you wanted the sine wave, right? You wanted this signal. You don't want all this noise. And so what you would do is you would take that signal and you would pass it through a low pass filter. Preferably one with a response that would pass. I'm overlaying my frequency response now on this Fourier plot. I would pass all these frequencies up to this point, and then I would cut all of these frequencies. And so this frequency would be allowed to pass through, and this 100 kilohertz noise would get sent to 0. And so I would get something out that looks very much like just the signal that I originally wanted, which is this signal, right? And that would be great. But of course, like I said, we can never get a signal that is perfect, a frequency response for a filter that is perfect. We can get something that's more practical. So the blue one might not be practical, but the green might be something that's more practical, something that looks like this. And so as you see, I get a little bit of the red signal, not much. And so what I might end up with when all is said and done with a practical filter is I take this signal, I send it into, a low pass filter, just like this. That's the input to my filter. The output of my filter would look something like very small, maybe a very small amount of almost undetectable noise. And I would roughly have my sinusoid back that I originally wanted, right? And so, yeah, that was kind of all I wanted to get at in this video, is kind of showing you what a Fourier transform looks like, or a fast Fourier transform. So this would be called a fast Fourier transform, or FFT, fast Fourier transform, or Fourier transform up top. And it's important to note, you can use the FFT function in LT Spice if you ever want to see, if you ever have a signal that we're plotting, which by now you probably have had plenty of signals to mess around with. But the point is that the fast Fourier transform shows us which frequencies are present in my signal. So if I had, if I had some DC value, like this wasn't centered around 0, but rather it was centered around something like 1 volt, then I would see that DC present in my signal as well, because that would be, it's riding on an average DC value. That would be a DC that's present in my signal as well, and we would see that in the fast Fourier transform. We don't need to worry about Fourier. That wasn't the point of this video. I just wanted to show practically what it would look like if we needed to filter something, because we can have a signal that has multiple frequencies present in the same signal, right? This one has an overwhelming base frequency of 1 kilohertz, but it does have this annoying 100 kilohertz noise riding on that 1 kilohertz. And if we want to filter out that noise and just get left with our original sine wave again, we could use something like a low pass filter. Okay, so I'm going to go ahead and end this video. Just wanted to give a little bit of context for filtering, and I think the fast Fourier transform is a really helpful way to kind of visualize the frequencies present in a signal, and then overlaying the transfer function magnitude response kind of shows us like, okay, I want to pass this frequency, but I want to attenuate this other frequency, and then hopefully I get something like this at the output of my filter. That's kind of the idea of what we're doing here. Okay, so I'm going to go ahead and end this video. I think in the next couple of videos I might have some example problems. Is that right? Yeah, so I'm going to do a filter design example, which is pretty similar to what I showed here, and hopefully some more of this context pulls it all together for us. So I'm going to go ahead and end this video.